Hello, this lecture is based on the textbook Combinatorics and Graph Theory, section 113, Special Types of Graphs. A complete graph of order n is denoted by k sub n. So remember that order is the number of vertices. A complete graph is when there's an edge between every two vertices, and the number of edges would be n choose 2. And here are complete graphs where n is 2, 3, and 5. An empty graph would be where there's no edges at all. A regular graph is when for each vertex the number of degree is the same, and we say that G is regular of degree r, or r regular if the degree for all vertices is equal to r. So a complete graph of order n would be regular of degree n minus 1, and an empty graph would be regular of degree 0. Right, so in this example, this graph is 3 regular because each vertex is of degree 3. In this example, the graph is 4 regular because you can check that every vertex has degree 4. A cycle graph denoted by C sub n is simply a cycle on n vertices. Here's an example of the graph C7. It's a cycle on 7 vertices, and a path graph is simply a path on n vertices. We say that a graph is bipartite if its vertex set can be partitioned into two sets, call them x and y, in such a way that every edge of the graph has one n vertex in x and the other in y. And we say that x and y are partite sets. So this graph is bipartite because it's possible to partition the vertices. So here we partition the vertices into two sets, x and y, and you can see that for every edge, one n is in x and the other is in y. And this graph is also bipartite because, for example, I can say that these two vertices belong to y, and then these other two vertices belong to y, and you can check that each of the 4 edges satisfies the properties that one edge or one endpoint has to be in x and the other has to be in y. This third graph is also bipartite, so the ones that I have circled could be put in the set x, and then the rest could be put in the set y, and then you can check that every edge would have one endpoint in x and the other endpoint in y. But these 3 are non-bipartite graphs because it's not possible to partition the vertices into two sets such that the condition that every edge has one n vertex in x and the other in y is possible. A bipartite graph is called a complete bipartite graph if its edge set is of the form xy for all x in the set x and for all y in the set y. So that means that every possible connection of a vertex of set with a vertex of y is present in the graph. And this is the notation that we will use. Right, so this is the complete bipartite graph 2, 3. So this would be one set and this is the other set. This would be a complete bipartite K1, 4. Here's one set and the other set. And this is the complete bipartite graph 4, 4, where the partite sets each has cardinality 4. All right, so next we will talk about a characterization of bipartite graphs. For simplicity, we'll prove this for a connected graph. The theorem says that a graph with at least 2 vertices is bipartite if and only if it contains no odd cycles. And remember that a cycle is a closed path. So before we prove this, let's look at some examples. So in this graph is bipartite, and you can check that every cycle has length 4 or 6. And remember that length is the number of edges. For example, 1, 2, 3, 4 is a cycle, and you can check that there are cycles of length 6, but no odd cycles. This is also a bipartite graph. So here's one way to partition the sets, and you can check that every cycle has length 4 or 6. But in this graph, this is not bipartite, and of course, this is the cycle graph of length 5. So for the proof, let G be a graph with 2 or more vertices. So first prove the forward direction. So show that if G is bipartite, then G contains no odd cycles. So suppose G is bipartite with partite sets x and y. Let C be a cycle of the graph. Say C is this closed path, V1, V2, through Vk and back to V1. And our goal is to show that C has even length. And we can assume, without loss of generality, that V1, the first vertex, is in the set X. Since G is bipartite, by definition, every edge of G has one n vertex in X and the other in Y. And so the second vertex in our cycle, V2, must be in Y, and then the next vertex V3 must be in X, and the next vertex V4 must be in Y, and so on. So what that means is that the vertex in the cycle Vi is in the set X if and only if I is odd, and the vertex Vi in the cycle is in Y if and only if I is even. Since Vk is adjacent to V1, which is in X, and again, because G is bipartite, it must be that Vk is in Y. And from what we said here, K is even. And so C is an even cycle. So here is just an illustration of what we just did. So with this proof, we start with a V1, which we assume to be in X. And we have shown that for all, so let's say our cycle is V1, V2, V3, V4, and back to V1. So here we have shown that the even vertices in the cycle must be in Y. In this example, there's no cycle. And in this example, so here's one cycle, V1, V2, V3, V4, back to V1. And again, the odd vertices in the cycle are in X, and the even vertices in the cycle are in Y. So we showed the forward direction. So now let's do the other direction. So for the reverse direction of the theorem, suppose the graph G contains no odd cycles. And what we will show is that G is bipartite. And what does it mean to show that G is bipartite? So first, we will partition the vertex set of G into two sets, X and Y. And after that, we will show that every edge of G indeed has one end vertex in X and the other end vertex in Y. So for the first part, first just pick a vertex of G, any vertex, and define the set X to be the set of vertices of G such that the shortest path from X to V has even length, or we should say that A shortest path. And then let Y be the complement of X. So Y would be all of the other vertices that do not satisfy the requirement to be in X. So let's look at these examples. So if I had picked V to be this vertex, then I can check the length of a shortest path from V to that vertex, or vice versa. So for this vertex here, the length from this vertex to V is 1. And the same for all of the other vertices on the right side. They all have length 1, which is odd. But this vertex, the A shortest path from this vertex to V has length 2. And so this is actually the X, and the set on the right is the Y. And the same with example 2, the set on the left is X, and then the set on the right is Y, because you can check that for each vertex on the set on the right, a shortest path from that vertex to V has odd length. Right, and the same thing with example 3. So these two vertices should belong to Y, and then the other two vertices, V and this vertex, should belong to X. So so we have done what we said we would do for part 1. We have partitioned the vertex set of G into two sets, and now we will do the second part. So we will show that every edge of G has one end vertex in X and the other in Y. So I claim that no two vertices in X are adjacent to each other. So here's the proof of this claim. So suppose, for contradiction, that X and X prime are two adjacent vertices in X, the set X. If X is the same as V, then the shortest path from V to X prime has length 1, because we said that X and X prime are adjacent. This implies that X prime is not in the set X, contradicting the assumption that X prime is in the set X. So that means this is not true. And if X is the same as V, there's a typo here. If X prime is the same as V, then the shortest path from V to X has again length 1. This implies that X is not in V, or this implies that X is not in the set X, which contradicts the assumption that X is in the set X. So X cannot be V, and X prime also cannot be V. So we will now construct a cycle in G. Let P1 be a path from V to X of shortest length. In other words, P1 is a shortest V to X path. Say P is of this form, from V0, V1 to V2K, starting from V, ending at X. And let P2 be a path from V to X prime of shortest length. Say P2 starts at V, let's call it also W0, and then the next vertex is W1, and so on until W24, W2t, which is equal to x prime. And we know that k is 1 or larger and t is 1 or larger because we have shown earlier that x is not the same as v, and also x prime is not the same as v. And the paths P1 and P2 have v in common because v0 is the same as w0. So for some examples, imagine that P1 could be this path, and then P2 can be this path, where only the very first vertex are in common. Or P1 might be A, B, C, D, E, and P2 might be A, B, C, F, G, where the first three vertices are in common. Now let V prime be the last vertex common to P1 and P3, or P1 and P2. So in this example, V prime is the very first vertex, but in the second example, V prime is the third vertex. So to be more formal, let V prime be a vertex on both paths, P1, P2, such that the V prime to X path, let's call it P1 prime, and the V prime to X prime path, call it P2 prime, have only the vertex V prime in common. It must be that P1 prime is a shortest V prime to X path, and P2 prime is the shortest V prime to X prime path, and V prime is equal to Vi and equal to Wi for some I. So this means that the vertices of P1 prime and P2 prime are in fact distinct except for V1 or for Vi and Wi. And so we can take all of those vertices from P1 prime and P2 prime and join them together to form a path, because all of the vertices are distinct except for the first vertex. So going back to the two examples, if this is the situation, then I would just go backward, joining G, V, A, and then B, C, D, E to make a path. Or in this situation, this would be my P1 prime and this would be my P2 prime. And I would go backward, going G, F, C, D, E to make a path. So since we said at the beginning that X and X prime are adjacent, I can just take this path and add one more edge, the edge from X to X prime. And this is now a cycle. And the length, you can count this to be, so we have 2k minus I, and also 2t minus I, plus 1, and this 1 comes from the edge x to x prime, and this is the sum of odd plus odd plus odd, so this is odd. So we have constructed a cycle which is odd. This is a contradiction to the fact that G has no odd cycles. So our first assumption that the vertices x and x prime are adjacent must be false. So no two vertices in the set X are adjacent to each other. So this is the proof of claim 1. And we can use the same logic, which you can try on your own, to show that no two vertices in Y are adjacent to each other. Now, combining claim 1 and claim 2, every edge of the graph G must have one end vertex in X and the other in Y. Therefore, G is bipartite, and the partite sets are X and Y. Now, we want to discuss what it means for two graphs to be the same. So let's look at these two graphs, so left and right. So they look different, but it's possible to redraw these graphs so that they look the same. So one way to do this is you can say that this vertex A should be drawn like the graph on the right. So A goes to 1, and B goes to 2, and C goes to 8, D goes to 3, and so on. And you can check that you will actually get the same graph on the right. So this is the idea of the isomorphism of graphs. We say that two graphs are isomorphic if there exists a one-to-one correspondence between the vertices of one graph to the vertices of the other graph, so that for every pair of vertices, there's an edge between the two of them in the first graph, if and only if there is an edge between the two vertices that they map to in the second graph. Another way of saying this is that two graphs are isomorphic if there exists a mapping from one vertex set to another that preserves adjacencies, edge adjacencies. The mapping is called an isomorphism. And this was the map that I described earlier. And it's common to simply say that the two graphs are the same if there is such an isomorphism. So some facts about isomorphic graphs is that if they are isomorphic, then they have the same number of vertices and the same number of edges. And of course, the converse is not true. Another fact is that if they are isomorphic, then the degree sequences must be identical. And again, the converse is not true. So let's look at some exercises. So here, remember that k sub n is the complete graph on n vertices. So prove that this complete graph has n times n minus 1 over 2 edges. So you've actually done this before, but see if you can prove it again. And for the second exercise, so k sub r2 comma k sub r1 comma r2 is the complete bipartite graph, where one partite set has r1 vertices and then the other has r2 vertices. If this graph is regular, meaning all vertices have the same degree, prove that r1 is the same as r2. Alright, so for this exercise, prove that the two graphs below are not isomorphic. So one possible way to prove that two graphs are not isomorphic is to check the degree sequence. If they're different, then they cannot be isomorphic. So here the degrees is 1, and then here the degrees is 2, here the degree is 3. But it turns out that these two graphs have the same degree sequence. So we cannot use that to prove that they're isomorphic. But one thing you can do is check that for the first graph, every cycle is of length 4 or longer. But for the second graph, I can see that there is a cycle of length 3, for example. This cycle is length 3. And so that shows that the two graphs are not isomorphic. For this exercise, so two of these graphs are isomorphic, but one is not isomorphic to the other two. So we can try different ways to prove this. So one thing to notice is that each of the graph is 3 regular. So the number of vertices is 10. And the sum of the degrees is 10 times 3. And by the first theorem of graph theory, the number of edges is 15. So all of these are the same. So we cannot use these facts to prove like which one is isomorphic and which one is not. And so for the pair that is isomorphic, you should be able to give an appropriate 1-to-1 correspondence. So you should label the vertices of the two graphs and then say which vertex goes to which vertex on the second graph. But now let's talk about how to find the graph that is not isomorphic to the other two. So we can try the same trick as the previous exercise. So you can try to compute the length of the shortest cycles for this graph and the length of the shortest cycles for the other two